Okay, this is a problem that I did in a previous video by using energy conservation, and I'll just post a link to that real quick. In the energy conservation approach, we looked at the drop in gravitational potential energy for the hanging block, and then we realized that that energy was pumped into the kinetic energy of the block and the rotational kinetic energy of the disk, and we were able to solve for the final speed and the final angular speed of the disk. Now we're going to approach the same problem by using forces and torques. And the advantage to this is that it gives you the actual acceleration of the object. And that means you have every detail of the motion for the entire time it's moving, not just a before and after kind of picture. So I'm going to write down some things symbolically here. I have the force of gravity pulling down, mass of the block times g. And I have an acceleration for this block. And I want to indicate the direction of acceleration and use that as the positive direction in my force analysis. The other force on the hanging block is the tension in that string. So that's pulling up, and that's an unknown tension. And then that string connects to the disk back here, and it's coming off of the disk tangentially and exerting a torque as it does that. So I want to look at, I'm going to put it in the picture here real quick. Vectors are kind of overlapping, but I want to look at a side view of a circle so we can see what this is doing. So looking at the situation from the side, this is what we have. There's a tension in that string. It's pulling like this. It's automatically perpendicular to the lever arm. So the string is going to come off tangentially. The lever arm is the radius of the circle. And that allows me to write down what torque is exerted by that string. Then I apply the rotational version of Newton's second law, tau equals I alpha. And I can even plug in the moment of inertia of a disk. All right, so this simplifies to the tension in the string multiplied by the radius of the disk equals 1/2 mr squared times alpha. There's one additional thing to realize here. The block is accelerating downward with an acceleration of a. That means the string is accelerating downward with an acceleration of a, and it's not slipping on the edge of this disk, which means the edge of the disk has a tangential acceleration of a at this moment, and there's a relationship between tangential acceleration and angular acceleration, and this allows me to eliminate alpha from the torque equation. All right, so I get an equation for my disk that says tension times the radius of the disk is equal to 1/2 mr squared times alpha, which is a over r. This simplifies, by the way. One of the r's cancels, and then I can divide both sides by r. And now all the r's are gone, and I have t equals 1/2 mass of the disk times a. My second equation comes from just applying Newton's second law to the hanging block. And I have a downward force of mass of the block times g. I'm going to abbreviate that, call it mb times g, and an upward force of t on the block. That's the net force, and that's equal to the mass times the acceleration. Okay, now I've got a system of equations. T equals 1/2 mass of the disk times a, mass of the block times g minus t equals mass of the block times a. And I can add those two equations together and eliminate t. And on the left-hand side, I'm going to get the mass of the block times g, and on the right-hand side, I'm going to get 1/2 mass of the disk plus mass of the block, and I'm factoring an a out of this. Now I'm going to multiply both sides by 2 and then solve for a. So I get 2mb times g over mass of the disk plus 2 mass of the block. And I can plug in my numbers, and when I do that, I get an acceleration of 2.80 meters per second squared. I have to follow this up with a kinematics calculation because the real question is how fast is the block moving after it's fallen a distance of 1 meter? So I'm just going to say we're starting at 0. I'm going to call the distance I've gone x, and I'm going to say we're moving in the positive direction. And I have v squared equals v naught squared plus 2a times x minus x naught. And v squared is going to be twice the acceleration, which is 2.8. times x minus x naught. Well, we've moved 1 meter. So I multiply these numbers and take the square root, and I get that my final speed is 2.37 meters per second, which agrees with the analysis that we did using energy instead of using forces and accelerations. Finally, I want to know what the angular speed of the disk is. And again, I'm going to look at my side view here to think about that. I have the speed of the mass, this 2.37 meters per second. That means the string is moving at 2.37 meters per second. And the string is not slipping, so it must be moving exactly the same speed as the edge of the disk. So the tangential speed at the edge of the disk is 2.37, and I can relate these things with V equals R omega, and say that omega must be V, the tangential speed at the edge of the disk, divided by R, the radius of the disk. So I get 2.37 over 0.2, and I get my angular speed, and that comes out to 11.9 radians per second.